My name is Joey Echeverria. I'm the platform technical lead at a small startup called Rakana, and I'm going to be talking about streaming ETL. So first, some background. So as I said, I'm Joey. I work at Rakana. What does Rakana do? We build machine data management software. That means that we collect logs, server metrics from a company's entire infrastructure. So the big thing there is we're all about scalability. So our customers are typically pulling in 10 terabytes of logs per day or more. I used to work at Cloudera. That won't be a surprise. Our infrastructure is all built on top of Hadoop. And before that, I was at the National Security Agency. My general background is distributed systems, security, data processing, big data, all the fun buzzwords. And I wrote a book. If you're interested in Hadoop security, why? But seriously, you can go get this from O'Reilly. So some history of these kinds of data problems. A legacy data architecture, and I put legacy in quotes because this is legacy in the big data world, is you've got data producers that are using systems like Flume or Scoop to send their data over to Hadoop, which is like a giant distributed file system. They write the data there. And then you've got these processing engines that are doing batch computations or queries over it. So you have to first write the data to the file system, and then you can sort of query it in batches. This is great, except that you want to do things in real time. Everybody wants to do things in real time because it's real time. So this is what a more modern stream data-based architecture may look like. You still have data producers. They're going to produce to a pub subsystem like Kafka, or Twitter recently put distributed log into the Apache incubator. It's a very similar system. And then you've got these stream processing systems that are reading the data out of Kafka or subscribe to the data out of Kafka as the data is produced. So you no longer have latency that's measured in hours or days for doing your processing, but you can actually get it down to minutes or seconds or sub-seconds. In addition to the stream processing systems, you may just have Kafka consumers, which are sort of standalone processes that are reading from Kafka and sending it to some downstream data store. Typically, you still have HDFS in the mix. That's probably going to be your store of record. It's a great long-term store. And then ideally, you want those stream processing systems to actually power your real-time visualization. You don't want the data to have to hit your Hadoop file system before you can start sending results to your customers. So I'm going to zoom in a little bit to these three pieces here, Storm, Flink, and Spark streaming. And this is going to be a super, super high-level primer. I'm not going to go that much into theory or that much into detail on these systems, so I definitely recommend you read more or go to other meetups where they'll go into a lot more detail about how these systems all work. Stream processing in general. What do I mean by stream processing? I mean events are flowing in, or objects or records are flowing in, and you want to do something to them. I sort of abstract stream processing down to these stages. There's probably more or less depending on what you're actually doing. But by filter, I mean taking data and throwing away things that you don't care about. Extraction is taking sort of raw records or raw data and pulling out structured information from it. So people always talk about log data as being unstructured. That's actually not true. Log data is highly structured. It's just that usually when it's given to you as a bunch of bytes or as a file, and you have to parse it in order to understand the structure. Projection is basically taking a record and throwing away the fields or parts of the record that you don't care about, or basically taking data in one schema and adapting it to another. If you've done SQL-based processing, this is basically anytime you do a select and you're only selecting a subset of the columns, you're doing a projection. Aggregation is counting things or adding things up, or sometimes more advanced if you're doing percentiles. But basically, it's math. Join is when you've got two different data streams and you want to bring them together. And then modeling is all of that really advanced stuff that everyone really wants to do, which is where you turn your raw data into this magic box that will then predict the future for you. So I'm going to zoom in a little bit on filter, extract, and project. And for the rest of this talk, I'm going to summarize those as a group to what I call data transformation. So going back to those sort of 3 stream processing systems, Storm is like the granddaddy of them. It's been around the longest. It's described as a distributed real-time computation system, which doesn't really mean very much. But the way that Storm is packaged, every application or job is built together into something called a topology. Topologies operate over tuples. That's what Storm calls records or events. And the way that you get data into Storm is with what they call a spout. A spout is a source of a stream. It can be another stream processing system. It can be Kafka. It can be a socket that you have open where you're just netcatting data to it. And then bolts are sort of the arbitrary logic in between. And bolts can do any of those stream processing functions. They can do filtering. They can do aggregation. They can do joins. They can do arbitrary functions. So the idea here, though, is that Storm's a relatively low-level model. You have to do all of the work. You have to assemble the bolts. You have to write all the bolts. You have to hook up your spouts in order to get data in. It's not very turnkey from that perspective. Apache Spark's a little bit newer. It's also probably the project that has the most hype around it these days. It does both stream processing and batch processing. You'll sometimes hear the stream processing part of Spark called Spark streaming. The way that Spark breaks down its data is it takes a continuous stream of records and discretizes it into what they call a D stream. And a D stream is a sequence of RDDs. RDDs are what Spark uses for basically any table or collection of records. And the real difference between Spark streaming and other streaming systems is that it's inherently what's known as microbatch, which means that before any of your functions are called inside of your Spark streaming job, the data is going to be batched up into small windows or small chunks of data. And then you operate over those. The advantage is that you get very high throughput at some sacrifice of latency as you need to wait for some data to come in before you can start processing it. Apache Flink is actually very similar to Spark. It's also both a batch and a stream processing system. It's a little bit newer than Spark. Spark was started, I want to say, in 2008 at Berkeley, but I may have that year wrong. Flink, I think, first came out in around 2011. They have similar abstractions. They call their stream of data a data stream, which is an unbounded collection of records. Unlike Spark streaming, Flink's streaming support is not microbatch. It is record at a time, which is also the way that Storm works. And when you're building up your Flink streaming applications, you can explicitly do record at a time processing, or you can specify that you want to do it over Windows. That's very useful if you're doing any kind of real-time processing on event data that has timestamps, and you want to calculate an aggregate rolling window for the last 5 minutes or something like that. I also mentioned Kafka before, but I haven't really explained it. It's a pub/sub messaging system implemented as a distributed log. It's very popular as a source and a sink for stream processing applications. It's very high speed. It has great scalability, great durability, and very easy to understand delivery guarantees. For the most part, it does at least once delivery, which means that it can send you duplicate data under certain failure scenarios, but it won't lose data so long as the system is configured correctly. You also may have heard of something called Kafka Streams, which is a relatively new addition to Kafka. It's actually a separate library and system for doing stream processing. It's actually kind of a competitor to Storm and Flink and Spark, but it's much newer. I haven't played with it, but any of these stream processing systems, you should feel free to make use of or play around with. All right, so that sort of lays the groundwork on stream processing. So let's go back to data transformation. So I explained this before, but I'll just reiterate. The first phase of data transformation is filtering. That's where I'm taking these multicolored blocks and only returning blue blocks. Extraction is taking what I view as unstructured data, applying parsing rules to it, and then creating a structured view of the data on the other side. And then projection is basically adapting the data from one schema to another. So in this case, I'm taking out some of the fields that are in the attributes, some of the fields that are part of sort of the top level, and then I'm creating a new record with a new schema where everything is sort of flattened. So what's the problem with using these existing systems for doing this kind of data transformation? Well, first you have to think about who's interested in doing data transformation. Yes, it's software developers. They need to do it. It may be data engineers that are not full-time software developers, but do a lot of software development as part of their sort of data science engineering work. It could be a sysadmin that just wants to lightly process the logs as they're coming in. They're not really someone that's going to develop a full-bore Java application. This is someone that really understands how to configure things, understands how to do scripting, lives a lot in the terminal. Or maybe an analyst that's very high level that just wants to modify the data before it goes into their analysis process. So the tools that you have available when you're using any of these stream processing systems are usually full programming languages. You've got Scala, Python, Java are the most popular. These tools are great, but not everybody is a programmer. Not everybody is a developer. A lot of people want to do these types of ETL or transformation tasks without having to dip down into a programming language to do it. This is a great quote from Josh Wills. If you don't know who Josh Wills is, he's, I believe, the director of data science at Slack. And this is stolen from a video presentation he gave at Midwest I/O in 2014, talking about feature engineering. Anyone that's ever worked on a data science project knows that the dirty secret is that only 5% of it is the fun math part where you're doing really advanced analysis using the latest techniques. The other 95% of it is all ETL. It's all figuring out how you turn that raw data into the features that makes the math work. So what's the solution? So what we've built is something that we call Workana Transform. It's a library. It's implemented in Java. That means you can embed it in any JVM language. It relies on another library that we wrote called Workana Configuration. Workana Configuration is basically what you want out of any arbitrary configuration language, which is you start with JSON. You add the ability to do comments, because writing configuration files without comments is silly. You actually have specific numeric types. Not every number is just a number. You actually have doubles and floats and things like that. And then you remove all of the excessive quoting that you need to do in JSON. So it's a lot less verbose and a lot easier to type. So I'm going to talk briefly about the data model. This is not required by the transformation engine that we've written, but it is the data model that we use internally, and it will help a lot of these other examples make sense. Every event has a globally unique ID. The ID is actually built as a hash of the other attributes and fields in the event. Every event has a timestamp. That's very important for us. You can only really understand log data if you know when it happened. Every event has an event type ID. That allows us to apply schema information over this sort of common schema after the fact. So everything coming through our system uses this single schema, but you'll see the very last field there is our attributes, which is just a map of keys to values. The event type ID allows us to interpret the body or to interpret those attributes in a specific way. Location is basically where the event was generated from. It can be a data center ID. It could be a rack location. It could be a hierarchy of data center rack or data center row rack, whatever makes sense for your specific environment. Host is the host name or IP address where the data originated from. Service is the service or process name that generated the data. And then body is the only really, really required besides timestamp part of an event, and that is just the raw event contents. So we tend not to explicitly interpret body unless we're doing one of these explicit transformation steps on it, where we're doing like data extraction and trying to pull information out and put it into the structured part of the event, which are the attribute key value pairs. So here's an example of something that you may get from syslog. If you haven't worked with syslog before, it's basically one of the oldest network-based logging protocols that's out there. And so we're taking that raw body, we're extracting some syslog information from it. In particular, the severity and facility is actually embedded in that 36 that's in the angle brackets at the beginning of the body, and a couple of other details that are getting pulled out. But this is just what one of our events look like. Hopefully this makes sense. If there are any questions, just stop me. So I'm going to show a couple of examples of how we actually use our transformation engine to do some processing on this kind of log data. The first one example will do some filtering. It's going to throw away some of the logs and only keep ones that we care about. It's going to extract some additional metadata from those logs, and then it's going to flatten the event from that structure that has the embedded attribute map to a schema that has all of the fields as top-level fields. So specifically, we're going to be filtering out events that don't have type ID 100. That's the type ID used for syslog messages. We're going to filter out events where the host name doesn't start with the letters EX. We're going to extract a numeric prefix from the syslog message. So it's not the beginning of the body, but that's actually the message that's the sort of payload part of the syslog. And we're going to flatten the syslog attributes and the extracted field into a new Avro schema. This is what the overall computation looks like. First, we load the event. So this will make a little bit more sense when I talk about the sort of architecture of the transformation engine and how the library is built. But basically, all you need to know right now is that the event is loaded into a single variable into the context that all of these actions is reading from. And what load event does is basically take all of those individual fields and turn them into top-level variables so they're easier to access later on. Filter is how we filter. In this particular case, we're looking for the event type ID and comparing it to the constant 100. Regex is how we extract the hostname prefix. I'll go into more details of how that gets configured in a second. We do a second filter. This host prefix.match.group.1 is actually referencing data that the regex action produced. So basically, any one of these actions can modify data in a global variable context, and then any subsequent action can then access that data. So we're going to filter things that start with EX. We're going to do a second regular expression match, this time to grab that numeric prefix. Then we're going to build the Avro record using the new schema. And then finally, we're going to save the output so that the program where this is embedded can take that new Avro record and then do whatever other processing or storage it wants to do with it. So specifically going into the first hostname prefix extraction, it's pretty simple. You give a regular expression pattern. In this case, we're looking for any two characters at the beginning of the string. We're matching those characters. And then the rest of the string we don't care about. The value that we're matching against is going to be the syslog hostname attribute. And then the destination is host prefix. And it's called destination, but it's actually a prefix for variables that will get automatically created by this action. So all of the matches get turned into match.group.number based on the parentheses that you have in there. Match group 0 is the entire string. There's also a Boolean on whether or not it matched at all that you can also access. So for the hostname prefix, the numeric prefix, it's the same kind of thing. After we've filtered by the host name matching the letters E and X, we're going to apply another regex pattern. This time, we're just looking for an arbitrary number of numbers at the beginning of the string. That's going to go against the syslog message attribute. And this time, our destination prefix is going to be just MSG. The other thing that this is showing is that for regular expression matches, the previous example, if the regular expression didn't match, which basically would only happen if your if your host name was less than 2 characters, then the data processing will just stop. It'll just kick out. It acts like another filter. In this case, we don't want to stop processing if it doesn't match. We want to continue no matter what, but we want to do different things. So if we do match the regular expression, we want to set the value of the extracted field to the part of the regular expression that matched. And if we don't match the regular expression, we just want to set it to an empty string. So this gives you some ability to control the flow of the data through the system and sort of decide when you want to stop processing an event. This one looks complicated, but it's relatively simple. This is all just taking the data that we have in the context and mapping it to the fields of our Avro schema. So this is a way of building up a new Avro record with a different schema. Our customers have used this, especially before Impala supported nested data types. The reason was that they wanted to be able to store the Avro data in a Parquet or Avro-based data set and do SQL queries over it, and very low latency SQL queries. So they would often flatten some of the log data in order to further process it. That's not as required, but sometimes you do want to build sort of purpose-built tables in your system where you may have a different schema than the raw event schema that we're sending data over the wire with. So the next example is extracting metrics from logs. This is actually very, very, very important for our use cases. A lot of log data contains numbers in it, and those numbers actually mean something. And if all you do is extract the logs and write them to a search engine, then those numbers aren't very useful to you. So the specific example is going to work with HTTP status logs. We're going to extract the request latency, basically the amount of time that this HTTP request took, as well as counts of HTTP status codes. So for every HTTP return code that's in the system, I want to know how many were 200, how many were 400, how many were 403, what have you. And very quickly, there are 2 different types of metrics that we can extract in our system. One is a gauge. You can think of a gauge as your speedometer on your car, which is something where you read the current value that tells you what the value is right now. But if you read it a little bit later, it'll just be updated to the entire new value. So to understand what's happening with that value over time, you just need to sort of look at the gauge at various points in time. A counter is a little bit different. A counter is something that you want to accumulate. It's not telling you what the total count is now. It's telling you the count since the last time you looked at it. So in particular, if you want to count something like HTTP status codes, for every event that comes in, you extract the status code out of it, and you want to count that status code with the number 1. And then our system has something that will aggregate those counts for further query and analysis later. This is an example of the output of this process, which is a metric event. We represent metrics in the same event schema that the rest of our system uses. Basically, we've got a custom event type ID, which is 107 for it. And then the attributes are metric name, and the values are a string version of the floating point value of that metric, and then the pipe and a letter to represent the type of metric, via a gauge or a counter metric. If you've ever worked with statsd, this is virtually identical to what their protocol is, just jammed into Avro objects. So the way that we do that is we load the event just as before. We're going to use this build metric action. The first thing we're going to do is build a gauge. The gauge metric is easily built by just taking the value in the latency attribute, converting it to a double, and then setting it to the http.request.latency metric name, and then storing that in the latency metric object. We then accumulate that output, so we want to make sure that that latency metric gets sent to the output of this process. For the second one, it's a little bit more complicated, but this is a dynamic counter mapping. Basically, the difference between the two is that in the first one, we have a very static name for the metric, whereas in the second one, we actually want to extract a value out of a field and turn that into the name of a metric. In this case, we want to take the status code and put it into the middle of the http.status.count string. So that way, a status code of 200 is going to become http.status.200.count, and 403 is going to be .403.count. This basically makes it very easy to do sort of dynamic creation of metrics, where part of the metric name is actually embedded in the data itself. And then we're going to set the value of that to 1, because in this case, we're just counting every event that has that status code. So talking a little bit about the architecture of this thing, it's actually fairly simple. Those configuration files, they get parsed one time when the system loads, and they actually get bound to these Java action objects. So basically, every top-level line here is an action, so everything here becomes its own Java object in the JVM. Then an important thing is that this library really needs a driver program of some kind in order to do things like initialize the context. That's how we actually get the data loaded into initially, as well as to do something with the output. So we've got a driver program that we embed into our system for any of the data that our Kafka consumers are consuming. So that way, any of the downstream systems where we need to send the data that's flowing through Kafka, we can run it through this engine before it gets to its destination. If you were embedding this into your own program, this would just be a small bit of work for Spark or Flink or whatever you're using in order to basically do, like, instantiate the parser and generate all of these objects. And then actually piping data through it's pretty easy. Basically, after you've initialized the context, there's just an execute action that happens at the very top, and the rest of it is handled for you. So all of the flow of control between those actions is automatically built up by the action tree that the parser is generating. And then the actions themselves can read and write variables in that global context. And then when you're done, you can copy the output out to the rest of your processing. We do support loading of custom actions. We use the Java Services Framework, which is basically some extra metadata that you include in your jar file to tell us that this is an action that you want to be able to use. You drop the jar file into your class path, and then that's all that's necessary for it to be registered from our perspective. Any custom actions appear as top-level actions. There's nothing special about the built-in actions versus ones that you register yourself. In fact, all of the built-in actions are registered through the same Java Services Framework that plugins use. There's basically two different methods you need to implement. There's an execute method on the action itself. That's basically what the action's going to do. And then there's something called an action builder, which is actually what binds to the configuration language and ends up building your action objects. And there's a build method that you have to implement for that. So some examples of custom actions that our customers have used or created. It can be for parsing custom log formats, something that's not easy to do with a regular expression, for example. So Cisco ACS, Citrix, Juniper. A lot of our customers have custom log formats that you've never seen before. And so they may need to work with us to have a custom action for parsing that kind of data. We also use it a lot for doing lookup of data in the stream. So a common one is looking up IP addresses in a GeoIP database. So you've got some log data that's coming in that has IP addresses, maybe from your customers hitting your website. You want to have some semblance of idea of where those IPs are coming from or where those customers are coming from. So you can do that lookup right there in the transformation engine. Or if you have any other kind of reference data set. So maybe your logs contain device IDs, but you actually want to translate that into a device name so that when you're looking at events in the UI, you can actually understand what you're looking at. So just kind of summarizing or bringing it back together, stream processing changes the way that you think about data. You no longer think about putting your data into a repository and then processing it or querying it, but you think about how you want to look at your data while it's in motion. Data transformation is the first step for any stream processing computation. You always need to do some form of filtering, extraction, or projection in order for your data to make sense. Otherwise, everyone that does any kind of computation over the data is going to have to repeat all of those steps over again. One of the reasons why we built this library is that we want to be able to experiment with different stream processing frameworks. So we can embed this library in our direct Kafka consumers. We can embed it in Spark Streaming. We can embed it in Flink. And we don't have to redo any of those sort of preliminary data transformation steps. We can write one configuration and load it in any of those different contexts. And this also reduces your reliance on developers for doing those sort of first phases of your stream processing pipeline. If you've got folks that want to load their data into a stream and do some lightweight ETL on it, this is a tool that's relatively more accessible to them versus teaching them how to write a Spark job from scratch. And then the biggest one for us is that reusing of the transformation logic. We have many different consumers that may be pulling our data out of Kafka, and we want to make sure that any of those consumers that need a particular transformation applied have the option of applying that transformation as they're reading the data. So right now, this is proprietary, but we are going to be releasing it under the Apache software license soon. The configuration library that this is based on, which sort of is that JSON-like language, is available today. So if you're interested in that, that's up on GitHub, and you can pull it down and play with it. With that, we have plenty of time for questions. Hi. Oh, sure. Any other questions? Yes. Yes, so we can do, I described it as reference data set lookups. So we don't do streaming joins, so we don't join two streams together. That's not a use case for our transformation engine. We will do a stream of records that's coming in, and we want to look up in some reference data set. And so that's kind of like a join, but very simplified because one of the tables that you're joining against is very small and isn't an actual stream. So yeah, we don't do joins in the transformation library itself. Any kind of joining of streams happens in the higher level stream processing framework.
Which stream processing system do you think is the best?
So the question was, which stream processing system do I think is the best? Because I'm being recorded, the answer is, of course, all of them. In reality, I don't actually know. We play a lot with Spark Streaming. We're playing around with Flink. They all have benefits and drawbacks. I would recommend just looking at them, comparing them for your use cases. Another great option is if you're not sure what you want to adopt, there's a project called Apache Beam, which is a general purpose API for stream processing frameworks that came out of Google. And it can work with Flink, Spark Streaming, I think Storm, I could be wrong on that one. Google's data flow engine, I think that's what it's called, which is part of their Google Cloud offering. So that's an API that you can use for doing stream processing, where you can change the execution engine later. So if you're not really sure which one you want to rely on, building against Apache Beam may give you some flexibility to migrate to different frameworks down the road. Any other questions? All right, thank you very much.